the closing of the intervening ocean basin, a small crustal fragment, which now forms southern Tibet, reached the trench and was accreted to Asia. This event was followed by the docking of India itself. Watch animation, Convergent Boundaries, India, Eurasia collision. As the intervening ocean basin was closing up, the more deformable materials on the continental margins of these land masses became highly folded and faulted. Two major thrust faults and many smaller ones sliced through the Indian crust. Subsequent motion along these thrust faults caused slices of the Indian crust to be stacked one upon the other. Today, these slices make up the bulk of the highest peaks in the Himalayas, many of which are capped by tropical marine limestones that formed along what was once the continental shelf. The formation of the Himalayas was followed by a period of uplift that raised the Tibetan plateau. Seismic evidence suggests that a portion of the Indian subcontinent was thrust beneath Tibet, a distance of perhaps 400 kilometers. If this occurred, the added crustal thickness would account for the lofty landscape of southern Tibet, which has an average elevation of more than 4,500 meters, higher than the tallest mountain in the contiguous United States. The collision with Asia slowed but did not stop the northward movement of India, which has since penetrated at least 2,000 kilometers into the mainland of Asia. Crustal shortening and thickening accommodated some of this motion. Much of the remaining penetration into Asia caused lateral displacement of large blocks of the Asian crust by a mechanism described as escape tectonics. As shown in Figure 11.30, when India continued its northward trek, parts of Asia were squeezed eastward out of the collision zone. These displaced crustal blocks include much of Southeast Asia and sections of China. Smart Figure 11.30 Full alternative text description. Smart Figure 11.30 India's continued northward migration severely deformed much of China and Southeast Asia. Watch tutorial, Himalayas. Why was the interior of Asia deformed to such a large extent, while India has remained essentially intact? The answer lies in the nature of these diverse crustal blocks. Much of India is a continental shield composed mainly of old Precambrian rocks. This thick, cold slab of crustal material has been intact for more than 2 billion years and is mechanically strong as a result. By contrast, Southeast Asia was assembled more recently, from the collision of several smaller crustal fragments. Consequently, it is still relatively warm and weak from recent periods of mountain building. Did you know? Edmund Hillary of New Zealand and Tenzing Norgay of Nepal were the first to reach the summit of Mount Everest on May 29, 1953. On their way up, they crossed a major Himalayan detachment fault, recognizable in movies like Everest by the prominent yellow band its footwall traces across the mountainside. The Appalachians. The Appalachian Mountains provide great scenic beauty near the eastern margin of North America, from Alabama to Newfoundland. Mountain belts of similar origin that formed during the same period and were once contiguous are found in the British Isles, Scandinavia, northwestern Africa, and Greenland. The orogenes that generated this extensive mountain system lasted a few 100 million years and resulted in the assembly of the supercontinent Pangaea. Detailed studies of the Appalachians indicate that this mountain belt was the result of 3 distinct episodes of mountain building. Our simplified overview begins roughly 750 million years ago, with the breakup of a supercontinent called Rodinia that predates Pangaea. Similar to the breakup of Pangaea, this episode of continental rifting and seafloor spreading generated a new ocean between the rift continental blocks. Located within this widening ocean basin was a microcontinent near the edge of ancestral Africa. About 600 million years ago, for reasons geologists do not completely understand, plate motion changed dramatically, and this ancient ocean basin began to close. This led to the development of multiple subduction zones, and the stage was now set for the 3 orogenic events that would lead to the collision of North America and Africa. The Appalachians formed during the closing of a precursor to the Atlantic Ocean. This event involved 3 separate stages of mountain building that spanned more than 300 million years. Smart Figure 11.31 Formation of the Appalachian Mountains. Smart Figure 11.31 Full Alternative Text Description Watch Tutorial, Appalachians. Tectonic orogeny. Around 450 million years ago, the marginal sea between the volcanic island arc and ancestral North America began to close. The collision that ensued, called the tectonic orogeny, caused the volcanic arc along with ocean sediments located on the upper plate to be accreted to the edge of the larger continental block. The remnants of this volcanic arc and oceanic sediments are recognized today as the metamorphic rocks through much of the Appalachian Mountain Belt. For example, schists beneath New York City and Washington, D.C., formed at this time. In addition to this pervasive regional metamorphism, numerous magma bodies intruded the crustal rocks along the entire continental margin. Akkadian orogeny. A second episode of mountain building, called the Akkadian orogeny, occurred about 350 million years ago. The continued closing of this ancient ocean basin resulted in the collision of a microcontinent with North America. This orogeny involved thrust faulting, metamorphism, and the intrusion of many large granite bodies. This event also added substantially to the width of North America, particularly in eastern New England. Alleghanian orogeny. The final orogeny, called the Alleghanian orogeny, occurred between 250 and 300 million years ago, when Africa collided with North America. This collision displaced material that was accreted earlier by as much as 250 kilometers toward the interior of North America. This event also displaced and further deformed the continental shelf sediments and sedimentary rocks that had once flanked the eastern margin of North America. Today these folded and thrust-faulted sandstones, limestones, and shales make up the largely unmetamorphosed rocks of the Valley and Ridge Province. This structural signature of mountain building can be found as far inland as central Pennsylvania and West Virginia. This region of the Appalachian Mountains consists of folded and faulted sedimentary strata that were displaced landward along thrust faults as a result of the collision of Africa with North America. Smart Figure 11.32 The Valley and Ridge Province. Smart Figure 11.32 Full Alternative Text Description. With the collision of Africa and North America, the young Appalachians, perhaps as majestic as the Himalayas, lay along the suture, in the interior of Pangaea. The tectonic forces that built the mountains ceased to drive them upward. Then, about 180 million years ago, the new supercontinent began to break into smaller fragments, a process that ultimately created the modern Atlantic Ocean. Because this new zone of rifting occurred east of the suture that formed when Africa and North America collided, remnants of Africa remain stuck to the North American plate. The crust underlying Florida is an example. Watch Mobile Field Trip, The Folded Rocks of Massanutten Mountain. Other mountain ranges built from continental collisions include the Alps and the Urals. The Alps formed as Africa and several smaller crustal fragments collided with Europe during the closing of the Tethys Sea. Similarly, the Urals were deformed and uplifted during the assembly of Pangaea, when northern Europe and northern Asia collided, forming a major portion of Eurasia. Unlike the Appalachian Belt, however, the Urals did not break apart again after their orogenesis. Concept checks 11.6. 1. Differentiate between terrain and terrain. 2. Explain why the continental crust of Asia was deformed more than that of the Indian subcontinent during the formation of the Himalayas. 3. Where and how might magma be generated in a newly formed collisional mountain belt? 4. How does the plate tectonics theory help explain the existence of fossil marine life in rocks atop collisional mountains? 11.7 Vertical motions of the crust. Explain the principle of isostasy and how it contributes to the elevated topography of mountain belts. Beyond the tectonic forces that move rocks laterally and thicken them vertically to produce mountainous topography, additional processes help to shape Earth's surface. As weathering and erosion work to lower mountains, a compensating process called isostasy causes them to rise, so they remain mountainous long after the tectonic processes that initially created them have ceased. Also, if tectonic processes raise a mountain belt too high, the rock at its core will become too weak to support the load, allowing the mountain to spread. The principle of isostasy. During the 1840s, researchers discovered that Earth's low-density crust floats on top of the high-density rocks of the mantle, much as wood floats in water. We will use the floating wooden blocks in Figure 11.33 to explore this idea. You can think of these blocks as a model mountain belt, floating in the mantle. Notice that only about 1/4 of each block projects above the water, and 3/4 is submerged. This is because wood is about 3/4 as dense as water. Similarly, most of the vertical thickness of a mountain belt forms a buoyant root that is submerged in the mantle, the remainder projects above the surrounding crust. This concept, that the crust floats in gravitational balance in the mantle, is called isostasy. This drawing shows how wooden blocks of different thicknesses float in water. In a similar manner, thick sections of crustal material float higher than thinner crustal slabs. Smart Figure 11.33 The principle of isostasy. Watch tutorial, Isostasy. Notice that the tallest of the floating blocks in Figure 11.33 stands the highest above the water surface and also sits the deepest. Similarly, the greater the crustal thickness of a mountain belt, the higher it will stand above sea level, and also the deeper its roots will be. Thus, the Himalayas, as the tallest range on Earth, also have the deepest roots. Did you know? Which is the tallest mountain on Earth? The answer depends on how you define tallest. Mount Everest, in the Himalayas, is of course the point on Earth's surface highest above sea level. However, Mauna Kea, a shield volcano on the Big Island of Hawaii, is the tallest peak as measured from the base of the mountain to the summit. Because Earth bulges outward along the equator, the peak of Chimborazo, in Ecuador, is the point on Earth's surface furthest from the center of the planet. Now, visualize what would happen if you placed a second small block on top of one of the blocks in Figure 11.33. The combined block would sink until it reached a new isostatic balance, at which point its top would be higher than before, and its bottom would be lower. This process of establishing a new gravitational balance in response to loading or unloading is called isostatic adjustment. Notice also that as a block rises or sinks, the surrounding water flows to accommodate it. Similarly, the highly viscous mantle will flow, albeit at an excruciatingly slow rate, when weight is added to or subtracted from the overlying crustal blocks. Applying the concept of isostatic adjustment, we should expect that when weight is added to the crust will respond by subsiding, causing the underlying mantle rocks to flow away. When the weight is removed, the crust will rebound, and the mantle rock will flow back underneath. Scientists have found evidence for crustal subsidence followed by isostatic rebound in areas formerly overlain by Ice Age glaciers. When continental ice sheets covered portions of North America during the Pleistocene epoch, ice masses that averaged about 3 kilometers thick added weight to the crust and caused downwarping by hundreds of meters. In the 8,000 years since this last ice sheet melted, gradual uplift of as much as 330 meters has occurred in Canada's Hudson Bay region, where the thickest ice had accumulated. One of the consequences of isostatic adjustment is that, as erosion cuts into a mountain range, removing mass, the range rises in response to the reduced load. In fact, because erosion removes material mainly by carving canyons and valleys rather than by uniformly wearing down mountain peaks, isostasy may actually push the peaks higher than their original height. This sequence illustrates how the combined effects of erosion and isostatic adjustment result in a thinning of the crust in mountainous regions. Smart Figure 11.3 for the effects of isostatic adjustment and erosion on mountainous topography. Smart Figure 11.3 for full alternative text description. The processes of uplift and erosion continue until the mountain block reaches average crustal thickness. When this occurs, these once elevated structures are near sea level, and the once deeply buried interior of the mountain is exposed at the surface. In addition, as mountains are worn down, the eroded sediment is deposited on adjacent landscapes, causing these areas to subside. How high is too high? Watch animation, isostatic adjustment. Where compressional forces are great, such as those driving India into Asia, lofty mountains such as the Himalayas result. Is there a limit on how high a mountain can rise? As mountaintops are elevated, gravity-driven processes such as erosion and mass wasting accelerate, carving the deformed strata into rugged landscapes. Equally important, however, is the fact that gravity also acts on the rocks within the mountain belt. The higher the mountain, the greater the downward force on rocks near the base. Eventually, the rocks deep within the developing mountain, which are relatively warm and weak, begin to flow laterally, as shown in Figure 11. 35. This process of gravitational collapse is analogous to what happens when a ladle of very thick pancake batter is poured onto a hot griddle. In addition to ductile spreading at depth, this process causes normal faulting and subsidence in the upper, brittle portion of Earth's crust. Without compressional forces to support them, mountains gradually collapse under their own weight. Gravitational collapse involves normal faulting in the upper, brittle portion of the crust and ductile spreading in the warm, weak rocks at depth. Figure 11.35 Gravitational collapse. Figure 11.35 Full alternative text description. Considering these factors, what keeps the Himalayas standing? Simply, the horizontal compressional forces that are driving India into Asia are greater than the vertical force of gravity. However, when India's northward trek ends, the downward pull of gravity, weathering, and erosion will become the dominant forces acting on this mountainous region. Concept checks 11.7. 1. Define isostasy. 2. Give one kind of evidence that supports the concept of isostatic uplift. 3. What happens to a floating object when weight is added? Subtracted? 4. Briefly describe how the principle of isostatic adjustment applies to changes in the elevations of mountains. 5. Explain the process whereby mountainous regions experience gravitational collapse. Concepts in review: crustal, deformation and mountain building. 11.1 Crustal deformation. Describe the three types of differential stress and identify the tectonic setting most commonly associated with each. Differentiate stress from strain and brittle from ductile deformation. Key terms: deformation, tectonic structure stress, confining pressure differential stress, compressional stress, tensional stress, shear, strain, elastic deformation, brittle deformation, ductile deformation. Tectonic structures are structures generated when rocks are deformed by bending or breaking. They include folds, faults, and joints. Stress is the force that drives rock deformation. When stress acts equally from all directions, we call it confining pressure. When the stress is greatest in one direction, we call it differential stress. There are three main types of differential stress: compressional, tensional, and shear. A rock's strength is its ability to resist permanent deformation. When the stresses on a rock exceed its strength, the rock deforms, usually by folding or faulting. Elastic deformation is caused by a temporary stretching of the chemical bonds in a rock. When the stress is released, the rock returns to its original shape. When the rock's strength is exceeded, bonds break, and the rock deforms in either a brittle or ductile fashion. Brittle deformation fractures rocks, whereas ductile deformation changes a rock's shape. Whether a rock deforms in a brittle or ductile manner depends on its temperature and its confining pressure. The hotter a rock, the more likely it is to experience ductile deformation. Greater confining pressure makes a rock stronger and less likely to break. Thus, rock deformation tends to be brittle in the shallow crust and ductile at deeper levels. Whether deformation is brittle or ductile also depends on the type of rock. For example, shale is weaker than granite, so it is more prone to ductile deformation. If a rock is forced to deform more quickly than can be accommodated by the slow processes of ductile deformation, it will break. Did the quarter on the left in the accompanying image experience brittle or ductile deformation? 11.2 Folds, rock structures formed by ductile deformation. List and describe 5 types of folds. Key terms: fold: anticline, syncline, dome, basin, monocline. Folds are wave-like undulations in layered rocks that develop through ductile deformation caused by compressional stresses. Anticlines usually arise by upfolding, or arching, of sedimentary layers, whereas synclines are downfolds, or troughs. Anticlines and synclines may be symmetrical, asymmetrical, overturned, or recumbent. When folded rocks erode to form a series of ridges and valleys, the ridges represent resistant beds, and the valleys represent softer beds. A fold is said to plunge when its axis penetrates the ground at an angle. This results in a V-shaped outcrop pattern. Domes and basins are large bowl or saucer-shaped folds that produce roughly circular outcrop patterns. When eroded, a dome has the oldest beds in the middle, and a basin has the oldest beds around the margin. Monoclines are large step-like folds in otherwise horizontal strata that develop when beds drape over a vertical offset produced by subsurface faulting. What name is given to the geologic structure shown in the accompanying image? 11.3 Faults and joints, structures formed by brittle deformation. Sketch and briefly describe the relative motion of rock bodies located on opposite sides of normal, reverse, and thrust faults as well as both types of strike-slip faults. Key terms. Fault dip-slip fault. Hanging wall block footwall block fault scarp normal fault block mountain horst graben half graben detachment fault reverse fault thrust fault strike-slip fault transform fault joint. Faults and joints are fractures in rock that form through brittle deformation. A fault is a fracture along which motion occurs, offsetting the rocks on either side. If the movement is in the direction of the fault's dip, the rock above the fault plane is the hanging wall block, and the rock below the fault is the footwall block. If the hanging wall moves down relative to the footwall, the fault is a normal fault. If the hanging wall moves up relative to the footwall, the fault is a reverse fault. Large normal faults with low dip angles are called detachment faults. Large reverse faults with low dip angles are thrust faults. Faults that intersect Earth's surface may produce a step in the land known as a fault scarp. Areas of tectonic extension, such as the Basin and Range Province, produce fault block mountains, horsts separated by neighboring grabens or half grabens. Areas of tectonic compression, such as mountain belts, are dominated by reverse faults that shorten the crust horizontally while thickening it vertically. Strike-slip faults have most of their movement in a horizontal direction, along the trend of the fault trace. Transform faults are strike-slip faults that serve as tectonic boundaries between lithospheric plates. Joints form in the shallow crust when rocks are stressed under brittle conditions. They facilitate groundwater movement and mineralization of economic resources, and they may result in hazards to humans. What type of rock structure is shown in each of the accompanying images, faults or joints? Explain how you arrived at your answer. 11.4 Mountain building. Locate and name Earth's major mountain belts on a world map. Key terms. Orogenesis, orogeny. Collisional mountain. Orogenesis is the making of mountains. An episode of orogenesis is an orogeny. Most orogenesis occurs along convergent plate boundaries, where compressional forces cause folding and faulting, thickening the crust vertically and shortening it horizontally. Look at the South American plate on the map. Explain why the Andes Mountains are located on the western margin of South America rather than the eastern margin. 11.5 Subduction and mountain building. Sketch a cross-section of an Andean-type mountain belt and describe how its major features are generated. Key terms. Accretionary wedge forearc basin. The type of convergent margin determines the type of mountains that form. Where one oceanic plate overrides another, a volcanic island arc forms. Where an oceanic plate subducts under a continent, Andean-type mountain building occurs. In either case, release of water from the subducted slab triggers melting in the overlying mangle wedge, generating basaltic magmas that rise to the base of the continental crust, where they often pond. The hot basaltic magma may heat the overlying crustal rocks sufficiently to generate a silica-rich magma of intermediate or felsic composition. Sediment scraped off the subducting plate builds an accretionary wedge. Between the accretionary wedge and the volcanic arc is a relatively calm site of sedimentary deposition, the Forearc Basin. The geography of Central California preserves an accretionary wedge, a forearc basin, and the roots of an Andean-style mountain belt. 11.6 Collisional mountain belts. Summarize the stages in the development of an alpine-type mountain belt such as the Appalachians. Key terms. Terrane microcontinent suture. A terrane is a relatively small crustal fragment that has been carried by an oceanic plate to a continental subduction zone and then accreted onto the continental margin. The North American Cordillera formed by the accretion of many successive terranes. The Himalayas and Appalachians were formed by collisions between continents when the intervening ocean basin subducted completely. The Appalachians were caused by the collision of ancestral North America with ancestral Africa more than 250 million years ago. The Himalayas were formed by the collision of India and Eurasia starting around 50 million years ago and are still rising. 11.7 Vertical motions of the crust. Explain the principle of isostasy and how it contributes to the elevated topography of mountain belts. Key terms. Isostasy. Isostatic adjustment, gravitational collapse. Earth's crust floats in the denser material of the mantle the way wood floats in water. If additional weight is placed on the crust, the crust sinks, and if weight is removed, the crust rebounds. This process of maintaining gravitational equilibrium is called isostatic adjustment. For a mountain belt, isostasy partially offsets the effect of erosion, pushing the mountains up as erosion wears them down. When compressional forces raise a mountain belt too high, the rock at the belt's core becomes warm and weak, and the belt spreads, becoming broader and lower. Based on the principle of isostasy, predict what will happen to the elevation of the highest peaks in a mountain range if rivers and glaciers erode deep valleys through the mountains, removing large amounts of rock. Give it some thought. 1. Refer to the accompanying diagrams to answer the following. What type of dip-slip fault is shown in Diagram 1? Were the dominant forces during faulting tensional, compressional, or shear? B. What type of dip-slip fault is shown in Diagram 2? Were the dominant forces during faulting tensional, compressional, or shear? C. Match the correct pair of arrows in Diagram 3 to the faults in Diagrams 1 and 2. Figure 11.9 to 1 Full alternative text description. 2. Refer to the accompanying photo to answer the following. A. The white line shows the approximate location of a fault that displaced these furrows created by a plow. What type of fault caused the offset shown? B. Is this a right lateral or left lateral fault? Explain. 3. Which of the three types of plate boundaries is primarily associated with normal faulting? Thrust faulting? Strike-slip faulting? 4. Suppose that a sliver of oceanic crust were discovered in the interior of a continent. Would this refute the theory of plate tectonics? Explain. 5. The accompanying photo, taken near the bottom of the Grand Canyon, shows a quartz vein that has been deformed. What type of deformation is exhibited, ductile or brittle? B. Did this deformation most likely occur near Earth's surface or at great depth? 6. Examine the diagrams depicting the structure of East Africa and the Canadian Rockies. A. Characterize the type of faulting found at each location and identify the differential stresses that produced these landforms. B. Along what type of plate boundary did each of these structures form? Figure 11.9 to 1 Full alternative text description. 7. Refer to the accompanying map, which shows the location of the Galapagos Rise and the Rio Grande Rise to answer the following questions. A. Name the types of continental margin found on the west and east coasts of South America. B. Based on your answer to question A, is the Galapagos Rise or the Rio Grande Rise more likely to end up accreted to a continent? Explain your choice. C. In the distant future, how might a geologist determine that this accreted landmass is distinct from the continental crust to which it accreted? 8. The Ural Mountains exhibit a north-south orientation through Eurasia. How does the theory of plate tectonics explain the existence of this mountain belt in the interior of an expansive landmass? 9. Briefly describe the major differences between the evolution of the Appalachian Mountains and the North American Cordillera. 10. Which of the accompanying sketches best illustrates an Andean type orogeny, a Cordilleran type orogeny, and an Alpine type orogeny? Figure 11.9 to 1 full alternative text description. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 12 Mass Movement on Slopes, the Work of Gravity. On March 22, 2014, a major landslide occurred near Oso, Washington. An extremely wet winter saturated older landslide deposits until they mobilized on a sunny Saturday morning. A large mass of mud and debris buried a 2.6 square kilometer area, damming a river, engulfing 49 buildings, and blocking a highway. The event claimed 43 lives. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 12.1 Describe how mass movement processes can cause natural disasters and discuss the role that mass movement plays in the development of landscapes. 12.2 Summarize the factors that control and trigger mass movement processes. 12.3 List and explain the criteria that are commonly used to classify mass movement processes. 12.4 Distinguish among rockfall, rockslide, debris avalanche, debris flow, slump, and earth flow. 12.5 Review the general characteristics of slow mass movement processes and describe the unique issues associated with a permafrost environment. Earth's surface is seldom perfectly flat but instead consists of slopes of many different varieties. Some are steep and cliff-like, others are moderate or gentle. Slopes can consist of barren rock and rubble or can be mantled with soil and covered by vegetation. Taken together, slopes are the most common elements in our physical landscape. Although most slopes may appear to be stable and unchanging, the force of gravity causes rock and soil to move downslope by the processes we call mass movement. At one extreme, the movement may consist of a roaring debris flow or a thundering rock avalanche. At the other extreme, it may be gradual and practically imperceptible. Landslides are a worldwide natural hazard. When these hazardous processes lead to loss of life and property, they become natural disasters. This chapter was revised with the assistance of Professor Scott Linneman, Western Washington University. 12.1 The importance of mass movement. Describe how mass movement processes can cause natural disasters and discuss the role that mass movement plays in the development of landscapes. Some mass movement processes are dangerous events that represent significant geologic hazards. Perhaps less well known is the fact that mass movement processes play an important role in the development and evolution of many of Earth's varied landscapes. The chapter opening photo is a striking example of a phenomenon that many people would call a landslide. For most of us, the word landslide implies a sudden event in which large quantities of rock and soil plunge down steep slopes. When people and communities are in the way, a natural disaster may result. Landslides constitute major geologic hazards that each year in the United States cause billions of dollars in damages and the loss of dozens of lives. As you will see, many landslides occur in connection with other major natural disasters, including earthquakes, volcanic eruptions, wildfires, and severe storms. Landslides are spectacular examples of a basic geologic process called mass movement. Mass movement refers to the downslope movement of rock, regolith, and soil under the direct influence of gravity. If you were to view several images of events called landslides, you would likely notice that the term seems to refer to several different things, from mudflows to rock avalanches. This variety reflects the fact that although many people, including geologists, frequently use the word landslide, the term has no specific definition in geology. Rather, it is a popular non-technical word used to describe any or all relatively rapid forms of mass movement. Landslides as geologic hazards. Though they are often used in the same conversation, hazard and risk have different meanings. A geologic hazard is a process that can cause harm to people or property if they are sufficiently exposed. Risk is the probability that exposure to a hazard will cause harm. Thus we can think of risk equals hazard exposure. Landslides are not just events that occur in remote mountains and canyons. People frequently live where rapid but rare mass movement events occur. Consequently, people living in susceptible areas often do not appreciate the risks of living where they do. However, media reports remind us that such events occur with some regularity around the world. Two examples are provided in Figure 12.1. In the example from Brazil, we see a city street buried in a mudflow that was triggered by heavy rains. By contrast, in El Salvador, steep slopes, weak rock, and the shock of an earthquake combined to produce a deadly event. In January 2011, following a period of torrential rains, a thick slurry of mud, appropriately called a mudflow, buried these cars in Nova Friburgo, Brazil. Heavy rains are an important trigger of mass movement processes. This deadly landslide that buried 300 homes in Santa Ticia, El Salvador, was triggered by an earthquake. Smart Figure 12.1. Landslides are geologic hazards. Watch mobile field trip, landslide. The role of mass movement in landscape development. In the evolution of most landscapes, mass movement is the step that follows weathering. Landscapes slowly change when rock and soil are removed from the places where they originate. Once weathering weakens and breaks apart rock, mass movement transfers the debris downslope, where a stream or glacier, acting as a conveyor belt, usually carries it away. Although there may be many intermediate stops along the way, most sediment is eventually transported to its ultimate destination, the sea. The combined effects of mass movement and running water produce stream valleys, which are among the most common and conspicuous of Earth's landforms. If streams alone were responsible for creating the valleys in which they flow, the valleys would be very narrow features. However, the fact that most river valleys are much wider than they are deep is a strong indication of the significance of mass movement processes in supplying material to streams. This is illustrated by the Grand Canyon. The walls of the canyon extend far from the Colorado River due to the transfer of weathered debris downslope to the river and its tributaries by mass movement processes. In this manner, streams and mass movement combine to modify and sculpt the surface. Of course, glaciers, groundwater, waves, and wind are also important agents in shaping landforms and developing landscapes. Smart Figure 12.2. Excavating the Grand Canyon. The walls of the canyon extend far from the channel of the Colorado River. This results primarily from the transfer of weathered debris downslope to the river and its tributaries by mass movement processes. Smart Figure 12.2. Full alternative text description. Watch tutorial, Mass wasting in the Grand Canyon. Slopes change through time. It is clear that if mass movement is to occur, there must be slopes that rock, soil, and regolith can move down. Earth's mountain building and volcanic processes produce these slopes through sporadic changes in the elevations of land masses and the ocean floor. If dynamic internal processes did not continually produce regions having higher elevations, the system that moves debris to lower elevations would gradually slow and eventually cease. Most rapid and spectacular mass movement events occur in areas of rugged, geologically young mountains. Newly formed mountains are rapidly eroded by rivers and glaciers into regions characterized by steep and unstable slopes. These areas often include valleys in thick deposits of unconsolidated material. It is in such settings that many massive destructive landslides, such as the ones described at the beginning of the chapter, occur. As mountain building subsides, mass movement and erosional processes lower the land. Through time, steep and rugged mountain slopes give way to gentler, more subdued terrain. Thus, as a landscape ages, massive and rapid mass movement processes give way to smaller, less dramatic downslope movements that are often imperceptibly slow. Concept checks 12.1. 1. Define mass movement. How does mass movement differ from erosional agents such as streams, glaciers, and wind? 2. In what sort of landscape are rapid mass movement processes most likely to occur? Describe how these geologic hazards might become geologic risks. 3. Sketch or describe how mass movement combines with stream erosion to expand valleys. 12.2 Controls and triggers of mass movement. Summarize the factors that control and trigger mass movement processes. Whether a slope fails depends on the relative size of the force pulling material downslope and the resisting strength of the rock or soil. While gravity is the driving force of mass movement, several factors play important roles in overcoming friction and material strength to create downslope movements. Long before a landslide occurs, various processes work to weaken slope material, gradually making it more and more susceptible to the pull of gravity. During this span, the slope appears stable but gets closer and closer to being unstable. Eventually, the strength of the slope is sufficiently weakened, or the slope becomes steeper, to the point that something causes it to cross the threshold from stability to instability. Such an event that initiates downslope movement is called a trigger. Remember that a trigger is not the sole cause of a mass movement event but just the last of many causes. Among the common factors that trigger mass movement processes are saturation of material with water, oversteepening of slopes, removal of anchoring vegetation, and ground vibrations from earthquakes. Many rapid mass movement events occur without discernible triggers. Slope materials gradually weaken over time under the influence of long-term weathering, infiltration of water, and other physical processes. Eventually, if the strength falls below what is necessary to maintain slope stability, a landslide will occur. The timing of such events is random, and thus accurate prediction is impossible. The role of water. Mass movement is sometimes triggered when heavy rains or periods of snowmelt saturate surface materials. The water does not transport the material. Rather, it allows gravity to more easily set the material in motion. This was the case in January 2005, when a massive debris flow swept through La Conchita, California, a small coastal community northwest of Los Angeles. Like the Oso landslide shown in the chapter opening photo, the La Conchita debris flow happened when older landslide deposits on the hillside became saturated during a winter of unusually high precipitation. On January 10, 2005, a massive debris flow, originating from the saturated deposits of a 1995 landslide, swept through La Conchita, California, a small coastal town situated on a narrow coastal strip between the shoreline and a steep bluff. The event, which occurred after a span of near-record rainfall, killed 10 people and destroyed many homes. Figure 12.3 Heavy rains trigger debris flows. Figure 12.3 Full alternative text description. When the pores in sediment become filled with water, the cohesion among particles is decreased, and they can move past one another with relative ease. For example, when sand is slightly moist, it sticks together quite well. However, if enough water is added to fill the openings between the grains, the sand will ooze out in all directions. Thus, saturation reduces the internal resistance of materials, which are then easily set in motion by the force of gravity. When clay is wetted, it becomes very slick, another example of the lubricating effect of water. Water also adds considerable weight to a mass of material. The added weight in itself may cause the downslope forces to exceed the resisting forces, which leads to the mass of material sliding or flowing downslope. Figure 12.4 Saturation reduces friction. When water saturates sediment, friction among particles is reduced, allowing material to move downslope. Figure 12.4 Full alternative text description. Oversteepened slopes. Oversteepening of slopes is another trigger of many mass movements. Oversteepening takes place in many situations. For example, as a stream cuts into a valley wall, it removes material from the base of the wall. The steeper slope increases the downslope forces and reduces the resisting forces, causing the material to fall or slide into the stream. Furthermore, through their activities, people often create oversteepened and unstable slopes that become prime sites for mass movement. Natural processes such as stream and wave erosion can oversteepen slopes. Changing the slope to accommodate a new house or road can also lead to instability and a destructive mass movement event. Loose, granular particles assume a stable slope called the angle of repose. This is the steepest angle at which loose material remains stable. Depending on the size and shape of the particles, the angle varies from 25 to 40 degrees. Larger, more angular particles maintain the steepest slopes. If the angle is increased, the rock debris adjusts by moving downslope. Figure 12.5 Unstable slopes. Figure 12.6 Angle of repose. The angle of repose is the steepest angle at which an accumulation of granular particles remains stable. Larger, more angular particles maintain the steepest slopes. Oversteepening is not just important because it triggers movements of unconsolidated granular materials. Oversteepening also produces unstable slopes and mass movements in cohesive soils, regolith, and bedrock because the steeper angle increases gravity's effect. The response is not immediate, as with loose, granular material, but sooner or later, one or more mass movement processes will eliminate the oversteepening and restore stability to the slope. Did you know? One of the most expensive landslides in history occurred April 10, 2013, in the Bingham Canyon open-pit copper mine in Utah. Careful monitoring of the oversteepened slope allowed the event to be predicted, which meant that the mining operations could be stopped and the mine evacuated, preventing loss of life. However, the loss of productivity cost the mine's owner an estimated $770 million. The landslide was the largest non-volcanic event in North America in modern times, moving 65 million cubic meters, enough rock to cover all of New York City's Central Park with 20 m of debris. Removal of vegetation. Plants protect against erosion and contribute to the stability of slopes because their root systems bind together soil and regolith. In addition, plants shield the soil surface from the erosional effects of raindrop impact. Where plants are lacking, mass movement is enhanced, especially if slopes are steep and water is plentiful. When anchoring vegetation is removed by forest fires or by people, surface materials frequently move downslope. An example illustrating the anchoring effect of plants occurred several decades ago, on steep slopes near Menton, France. Farmers replaced olive trees, which have deep roots, with a more profitable but shallow-rooted crop, carnations. When the less stable slope failed, the landslide took 11 lives. In July 1994, a severe wildfire swept Storm King Mountain, west of Glenwood Springs, Colorado, denuding the slopes of vegetation. 2 months later, heavy rains resulted in numerous debris flows, rapid mass movement events involving water-saturated rock and soil. One debris flow blocked Interstate 70 and threatened to dam the Colorado River. A 5-kilometer length of the highway was inundated with tons of rock, mud, and burned trees. The closure of Interstate 70 imposed costly delays on users of this major highway. Wildfires are inevitable in the western United States, and fast-moving, highly destructive debris flows triggered by intense rainfall are some of the most dangerous post-fire hazards. Such events are particularly dangerous because they tend to occur with little warning. Their mass and speed make them particularly destructive. Post-fire debris flows are most common in the 2 years after a fire. The very first intense rain event following a wildfire is likely to trigger a debris flow event. It takes much less rain to trigger debris flows in burned areas than in unburned areas. In Southern California, as little as 7 millimeters of rain in 30 minutes has triggered debris flows. In September 2014, this wildfire consumed 9,000 acres of dense forest on steep terrain near Fresh Pond, California. During the summer, wildfires are becoming more common in many parts of the western United States. Millions of acres are burned each year. The loss of anchoring vegetation sets the stage for increased mass movements and more sediment delivered to stream systems. Figure 12.7 Wildfires contribute to mass movement. In addition to eliminating plants that anchor the soil, fire can promote mass movement in other ways. Following a wildfire, the upper part of the soil may become dry and loose. As a result, even in dry weather, the soil tends to move down steep slopes. Moreover, fire can bake the ground, creating a water-repellent layer at a shallow depth. This nearly impermeable barrier prevents or slows the infiltration of water, resulting in increased surface runoff during rains. The result can be dangerous torrents of viscous mud and rock debris. Earthquakes as triggers. Conditions that favor mass movement may exist in an area for a long time without movement occurring. An additional factor is sometimes necessary to trigger the movement. Among the most important and dramatic triggers are earthquakes. An earthquake and its aftershocks can dislodge enormous volumes of rock and unconsolidated material. A major earthquake in Nepal in April 2015 triggered hundreds of landslides, which destroyed roads and blocked rivers. The damage shown here occurred in the village of Singati in northeastern Nepal. Figure 12.8 Earthquakes as triggers. Examples from plate boundaries, California and Nepal. A memorable U.S. example of an earthquake triggering mass movement occurred in January 1994, when a quake struck the Los Angeles region of Southern California. Named for its epicenter in the town of Northridge, the magnitude 6.7 event produced estimated losses of $20 billion. Some of the losses resulted from more than 11,000 landslides in an area of about 10,000 square kilometers that were set in motion by the quake. Most were shallow rockfalls and slides, but some were much larger and filled canyon bottoms with jumbles of soil, rock, and plant debris. The debris in canyon bottoms creates a secondary threat because it can mobilize during rainstorms, producing debris flows. Such flows are common and often disastrous in Southern California. On April 25, 2015, a magnitude 7.8 earthquake shook much of central Nepal. The earthquake and its aftershocks triggered thousands of landslides in the rugged Himalayas and caused nearly 8,900 fatalities. Rock avalanches and debris slides thundered down steep mountain slopes, burying buildings and blocking roads and rail lines. The landslides also dammed rivers, creating many lakes. Earthquake-created lakes present a dual danger. Apart from the upstream floods that occur as a lake builds behind the natural dam, the piles of rubble that form the dam may be unstable. Another quake, or simply the pressure of water behind it, could burst the dam, sending a wall of water downstream. Such floods may also occur when water begins to cascade over the top of the dam. Liquefaction. Intense ground shaking during earthquakes can cause water-saturated surface materials to lose their strength and behave as fluid-like masses that flow. This process, called liquefaction, was a major cause of property damage in Anchorage, Alaska, during the massive 1964 Good Friday earthquake, the largest quake to strike North America in the 20th century. Did you know? According to the U.S. Geological Survey, studies of debris flows from burned areas in Southern California and other western states have ranged in volume from as small as 800 yd3 to as large as 400,000 yd3. This larger volume is equivalent to 50,000 dump truck loads. The potential for landslides. Figure 12.9 shows the landslide potential for the contiguous United States. All states experience some damage from rapid mass movement processes, but it is obvious that not all areas of the country have the same landslide hazard potential. As you might expect, there are greater landslide risks in mountain areas. In the east, landslides are most common in the Appalachian Mountains. In the Pacific Northwest, water from winter rains and melting snow often trigger rapid forms of mass movement, including slumps in the glacial sediments that underlie Seattle's and Portland's hilly neighborhoods. Coastal California's steep slopes have a high landslide potential. Here mass movement events may be triggered by winter storms or by the ground shaking associated with earthquakes. Landslides are also triggered when strong wave activity undercuts and oversteepens coastal cliffs. Figure 12.9 Landslide potential in the contiguous 48 states. Figure 12.9 Full alternative text description. Did you know? Landslides are expensive. The U.S. Geological Survey estimates that the total losses from landslides each year in the United States are between $2 billion and $4 billion. This is a conservative estimate, as there is no uniform method or overall agency that keeps track of or reports landslide losses. Landslides result in extremely high monetary losses in other countries, too, but there are no reliable estimates of the amounts. A glance at the map shows that Florida and the adjacent Atlantic and Gulf coastal plains have some of the lowest landslide potentials because steep slopes are largely absent. In the center of the country, the plain states are relatively flat, so landslide potential is mostly low to moderate. High potential areas are along the steep bluffs that flank river valleys. Concept checks 12.2. 1. How does water affect mass movement processes? Compare the circumstances that led to the killer landslides at Oso, Washington, and La Conchita, California. 2. Describe the significance of the angle of repose. 3. How might a wildfire influence the risk of mass movement? 4. Describe the relationship between earthquakes and landslides. 5. What factors increase the risks of landslides? 12.3 Classification of mass movement. Processes. List and explain the criteria that are commonly used to classify mass movement processes. Geologists use the term mass movement to describe a broad array of different processes. Generally, the different types are classified based on the type of material involved, the kind of motion displayed, and the velocity of the movement. Type of material. The classification of mass movement processes on the basis of the material involved in the movement depends on whether the descending mass began as unconsolidated material or as bedrock. If soil and regolith dominate, terms such as debris, mud, or earth are used in the description. In contrast, when a mass of bedrock breaks loose and moves downslope, the term rock may be part of the description. Type of motion. In addition to characterizing the type of material involved in a mass movement event, the way in which the material moves may also be important. Generally, the kind of motion is described as either a fall, a slide, or a flow. Fall. When the movement in a mass movement event involves the free fall of detached individual pieces of any size, it is termed a fall. Fall is a common form of movement on slopes that are so steep that loose material cannot remain on the surface. The rock may fall directly to the base of the slope or move in a series of leaps and bounds over other rocks along the way. Rockfalls are the primary way in which talus slopes are built and maintained. Many falls result when freeze and thaw cycles and/or the action of plant roots reduce rock strength to the point that gravity overwhelms the resisting forces. Although signs along bedrock cuts on highways warn of falling rock, few of us have actually witnessed such an event in progress. However, as Figure 12.10 illustrates, they do indeed occur. This rockfall blocked a highway. Smart Figure 12.10 Watch out for falling rock. When large masses of rock plunge from great heights, they hit the ground with enormous force and often trigger additional mass movement events. One deadly example occurred in Peru. In May 1970, an earthquake caused a huge mass of rock and ice to break free from the precipitous north face of Nevada's Huascarán, the loftiest peak in the Peruvian Andes. The material plunged nearly a kilometer and pulverized on impact. The rock avalanche that followed rushed down the mountainside, made fluid by trapped air and ice. Along the way, it ripped loose millions of tons of additional debris that ultimately and tragically buried more than 20,000 people in the towns of Yungay and Ranraherka. A different effect, triggered by a rockfall, occurred in Yosemite National Park on July 10, 1996. When two large rock masses broke loose from steep cliffs and fell about 500 meters to the floor of Yosemite Valley, the impacts were great enough to be recorded at seismic stations 200 kilometers from the site. As the dislodged rock masses struck the ground, they generated atmospheric pressure waves that were comparable in velocity to a tornado or hurricane. The force of the air blasts uprooted and snapped more than 1,000 trees, including some that were 40 meters tall. Watch animation, mass movements, 5 main types. Slide. Many mass movement processes are described as slides. The term refers to mass movements in which there is a distinct zone of weakness separating the slide material from the more stable underlying material. Two basic types of slides are recognized. In rotational slides, the surface of rupture is a concave upward curve that resembles the shape of a spoon, and the descending material exhibits a downward and outward rotation. By contrast, in a translational slide, a mass of material moves along a relatively flat surface such as a joint, fault, or bedding plane. Such slides exhibit little rotation or backward tilting. Flow. The third type of movement common to mass movement processes is termed flow. Flow occurs when material moves downslope as a viscous, often turbulent, fluid. Most flows are saturated with water and typically move as lobes or tongues. Rate of movement. Some of the events that have been described so far involved very rapid rates of movement. For example, it is estimated that the debris that rushed down the slopes of Peru's Nevado's Huascarán moved at speeds in excess of 200 km per hour. This most rapid type of mass movement is termed a rock avalanche. Geologists used to think that rock avalanches, such as the one that produced the scene in Figure 12.11a, must literally float on air as they move downslope. That is, high velocities might result when air becomes trapped and compressed beneath the falling mass of debris, allowing it to move as a buoyant, flexible sheet across the surface. But more recent studies of landslide deposits on other planetary bodies have made us question this hypothesis. Similar deposits from long run-out landslides on Mars seem to have been lubricated by interactions of rock and water. The prehistoric Blackhawk rock avalanche is considered one of the largest non-volcanic landslides in North America. The Blackhawk event is just a fraction the size of the landslides in the Valles Marineris canyons of Mars. Water probably played an important role in both situations, allowing the deposits to extend so far from their sources. Figure 12.11 Landslides on Earth and Mars. Most mass movements, however, do not move with the speed of a rock avalanche. In fact, a great deal of mass movement is imperceptibly slow. One process that we will examine later, termed creep, results in particle movements that are usually measured in millimeters or centimeters per year. Thus, as you can see, rates of movement can be spectacularly sudden or exceptionally gradual. Although various types of mass movement are often classified as either rapid or slow, such a distinction is highly subjective because a wide range of rates exists between the two extremes. Even the velocity of a single process at a particular site can vary considerably. Did you know? The U.S. Geological Survey estimates that between 25 and 50 people are killed by landslides annually in the United States. The worldwide death toll is much higher. Concept checks 12.3. 1. List and sketch 3 ways material can move during mass movement. 2. How has scientific thinking changed about how rock avalanches move at such great speeds? 12.4 Common forms of mass movement, rapid to slow. Distinguish among rockfall, rockslide, debris avalanche, debris flow, slump, and earth flow. Classifying kinds of mass movement can be tricky because of the variable factors of speed, three-dimensional geometry, and type of material. The common mass movement processes discussed in this section are slump, rockslide, debris flow, and earth flow. They are most common where slopes are steep. The speed of movement varies from barely perceptible to very rapid. Slump refers to the downward sliding of a mass of rock or unconsolidated material moving as a unit along a curved surface. Usually the slumped material does not travel spectacularly fast, and it does not travel very far. Slump is a common form of mass movement, especially in thick accumulations of cohesive materials such as clay. The ruptured surface is characteristically spoon-shaped and concave upward or outward. As the movement occurs, a crescent-shaped scarp is created at the head, and the block's upper surface is sometimes tilted backward. Although slump may involve a single mass, it often consists of multiple blocks. Sometimes water collects between the base of the scarp and the top of the tilted block. As this water percolates downward along the ruptured surface, it may promote further instability and additional movement. Slump occurs when